computing, highlighting both the progress and the complexities involved in validating quantum supremacy claims. Skepticism. Despite high hopes for quantum computing, significant progress in hardware, and optimism about future applications, a 2023 Nature Spotlight article summarized current quantum computers as being, for now, good for absolutely nothing. The article elaborated that quantum computers are yet to be more useful or efficient than conventional computers in any case, though it also argued that in the long term such computers are likely to be useful. A 2023 Communications of the ACM article found that current quantum computing algorithms are insufficient for practical quantum advantage without significant improvements across the software-hardware stack. It argues that the most promising candidates for achieving speed-up with quantum computers are small data problems, for example in chemistry and materials science. However, the article also concludes that a large range of the potential applications it considered, such as machine learning, will not achieve quantum advantage with current quantum algorithms in the foreseeable future, and it identified I/O constraints that make speed-up unlikely for big data problems, unstructured linear systems, and database search based on Grover's algorithm. This state of affairs can be traced to several current and long-term considerations. Conventional computer hardware and algorithms are not only optimized for practical tasks, but are still improving rapidly, particularly GPU accelerators. Current quantum computing hardware generates only a limited amount of entanglement before getting overwhelmed by noise. Quantum algorithms provide speed-up over conventional algorithms only for some tasks, and matching these tasks with practical applications prove challenging. Some promising tasks and applications require resources far beyond those available today. In particular, processing large amounts of non-quantum data is a challenge for quantum computers. Some promising algorithms have been dequantized, i.e., their non-quantum analogs with similar complexity have been found. If quantum error correction is used to scale quantum computers to practical applications, its overhead may undermine speed-up offered by many quantum algorithms. Complexity analysis of algorithms sometimes makes abstract assumptions that do not hold in applications. For example, input data may not already be available encoded in quantum states, and oracle functions used in Grover's algorithm often have internal structure that can be exploited for faster algorithms. In particular, building computers with large numbers of qubits may be futile if those qubits are not connected well enough and cannot maintain sufficiently high degree of entanglement for long time. When trying to outperform conventional computers, quantum computing researchers often look for new tasks that can be solved on quantum computers, but this leaves the possibility that efficient non-quantum techniques will be developed in response, as seen for quantum supremacy demonstrations. Therefore, it is desirable to prove lower bounds on the complexity of best possible non-quantum algorithms, which may be unknown, and show that some quantum algorithms asymptomatically improve upon those bounds. Some researchers have expressed skepticism that scalable quantum computers could ever be built, typically because of the issue of maintaining coherence at large scales, but also for other reasons. Bill Unruh doubted the practicality of quantum computers in a paper published in 1994. Paul Davies argued that a 400-qubit computer would even come into conflict with the cosmological information bound implied by the holographic principle. Skeptics like Gil Khalai doubt that quantum supremacy will ever be achieved. Physicist Mikhail Diakonov has expressed skepticism of quantum computing as follows: so the number of continuous parameters describing the state of such a useful quantum computer at any given moment must be about 1,300. Could we ever learn to control the more than 1,300 continuously variable parameters defining the quantum state of such a system? My answer is simple: no, never. Physical realizations. A practical quantum computer must use a physical system as a programmable quantum register. Researchers are exploring several technologies as candidates for reliable qubit implementations. Superconductors and trapped ions are some of the most developed proposals, but experimentalists are considering other hardware possibilities as well. The first quantum logic gates were implemented with trapped ions, and prototype general-purpose machines with up to 20 qubits have been realized. However, the technology behind these devices combines complex vacuum equipment, lasers, microwave and radio frequency equipment, making full-scale processors difficult to integrate with standard computing equipment. Moreover, the trapped ion system itself has engineering challenges to overcome. The largest commercial systems are based on superconductor devices and have scaled to 2,000 qubits. However, the error rates for larger machines have been on the order of 5%. Technologically, these devices are all cryogenic, and scaling to large numbers of qubits requires wafer-scale integration, a serious engineering challenge by itself. Theory computability. Any computational problem solvable by a classical computer is also solvable by a quantum computer. Intuitively, this is because it is believed that all physical phenomena, including the operation of classical computers, can be described using quantum mechanics, which underlies the operation of quantum computers. Conversely, any problem solvable by a quantum computer is also solvable by a classical computer. It is possible to simulate both quantum and classical computers manually with just some paper and a pen, if given enough time. More formally, any quantum computer can be simulated by a Turing machine. In other words, quantum computers provide no additional power over classical computers in terms of computability. This means that quantum